There is a telescope in Chile that never stops watching. Each night, high up in the Atacama desert, it opens the largest digital camera ever constructed and gazes into the blackness. But it does not observe the universe the way other telescopes do. It does not lock onto a single galaxy and spend weeks studying it. It does not wait around for one flawless image. It does not freeze space into a still photograph. It watches everything over and over again. Every 3 nights, the Vera Rubin Observatory sweeps across the visible southern sky, hunting for anything that shifted, brightened, disappeared, detonated, or showed up somewhere nothing had any business being. And within its very first months, before its full mission had even properly gotten underway, it began uncovering things that had no right to be there. A single image holding 10 million galaxies, a stream of stars stretching 163,000 light-years from a spiral galaxy, more than 11,000 freshly identified asteroids, a spinning object so enormous and rotating so rapidly that the laws of physics say it should have ripped itself to pieces, a star in Andromeda that may have collapsed straight into darkness, and objects drifting in from other star systems, passing silently through ours like quiet visitors from places we could never hope to reach. Rubin was constructed to chart the universe, but what it caught first was something far more unsettling. Evidence that the sky is shifting faster than we are able to make sense of it. The Vera Rubin Observatory rests on a mountaintop in Chile beneath some of the driest and darkest skies found anywhere on Earth. Its mission carries the name the Legacy Survey of Space and Time. That name sounds measured, almost like something you would find in a textbook, but what it truly means is this. Rubin is assembling a 10-year motion picture of the universe. Not a snapshot, a motion picture. Every few nights, it sweeps across the entire visible sky above the southern hemisphere. Then it lays the new image alongside the previous one. If something has changed, Rubin catches it. A dot shifted, a star faded, a galaxy flared up, an asteroid emerged, something went missing, and every one of those changes becomes an alert. When Rubin's alert system was put to the test, it produced hundreds of thousands of alerts in a single night. Eventually, the observatory is expected to fire off millions of alerts every single night, each one pointing towards something in the sky that looks different from before. This is what sets Rubin apart from nearly every telescope humanity has ever put together. Hubble reshaped astronomy by revealing extraordinary detail. James Webb reshaped astronomy by showing us infrared light from the ancient universe. But Rubin is different. Rubin reshapes astronomy by giving the sky something it never had before: a memory. For thousands of years, people looked upward and saw patterns. Stars appeared fixed in place. Constellations seemed as though they would last forever. Galaxies looked distant and utterly quiet. The universe felt unhurried, almost completely still. But Rubin is showing us that this was never anything more than an illusion. The sky is alive with constant movement. Asteroids journey across the solar system. Stars blow themselves apart. Black holes may take shape without any warning at all. Objects from distant star systems come and go. Galaxies stretch, get torn, blend together, and expose structures too dim for earlier surveys to ever detect. And because Rubin keeps circling back to the same regions, it can pick up on changes that no single image could possibly expose on its own. This is the new frontier, not merely deep space, but space that is constantly changing. And the earliest results already made clear just how much we had been overlooking. On June 23, 2025, the world got its first look at images from Rubin, and one of those images was nearly impossible to take in. A single composite image of the Virgo cluster contained roughly 10 million galaxies. 10 million galaxies, not stars. Galaxies, each one potentially home to billions of stars, planets, black holes, nebulae, and worlds we know nothing about. And this was just one image, covering only a tiny sliver of what Rubin will eventually photograph. If you tried to look at every single galaxy in that one image for just 1 second each, no stopping, no sleeping, no blinking, it would take you months. And yet for Rubin, that was merely the starting point. The telescope is expected to survey billions of galaxies across its decade-long mission, assembling one of the most thorough maps of the cosmos ever created. But tucked inside those early images was something nobody anticipated. A stellar stream, a flowing river of stars being slowly pulled away from the spiral galaxy, Messier 61. It stretched 163,000 light-years across. That is wider than the entire diameter of the Milky Way, and nobody had any idea it was there. This is one of the core reasons Rubin is so remarkable. It does not simply detect bright, obvious objects. It can uncover faint structures spread over vast regions of sky, structures too wide, too dim, or too delicate for other telescopes to easily pick up. A stellar stream is not merely a stunning visual feature. It is proof of violence. It means gravity is ripping a system to pieces. A smaller galaxy or star cluster may have drifted too close to a larger one, and now its stars are being drawn out into a long cosmic trail. These streams are the fossil records of galactic destruction. They show us how galaxies grow, how they consume smaller systems, how invisible dark matter influences the movement of stars, and how the universe constructs large-scale structures through collision, gravity, and time. Rubin captured one that had been hiding in plain sight all along, a structure larger than our own galaxy, completely invisible until the right instrument looked with sufficient breadth, sufficient sensitivity, and sufficient patience. And that was only the first surprise. Even before its full mission officially got underway, Rubin had already identified more than 11,000 new asteroids. That alone would mark a historic achievement. But it is really only a preview of what is coming. Scientists anticipate that Rubin will discover around 1 million previously unknown asteroids within its very first year of full operation, roughly the same number that humanity managed to catalog across the previous 2 centuries. In just 12 months, Rubin could match centuries of asteroid discovery. That matters because asteroids are far more than floating rocks. They are leftover fragments from the early solar system. They carry within them records of planetary formation, collisions, migration, and the turbulent history of the space surrounding Earth. Some are completely harmless, some pass close to our planet, some may prove valuable for future missions, and some are strange enough to challenge everything we think we understand. One of them goes by the designation 2025 MN45. It is enormous, nearly twice the height of the Empire State Building. But its size is not actually what makes it so unsettling. What is unsettling is its rotation. This object completes one full spin every 1 minute and 53 seconds. For something that large, that is extraordinarily fast enough that centrifugal force ought to be tearing it apart. A rubble pile asteroid spinning at that rate should not be able to stay in one piece. It should be shedding material. It should be stretching, cracking, or breaking apart into scattered debris. And yet 2025 MN45 is still there, still spinning, still holding itself together. Why? Nobody can say for certain. Perhaps it is not a loose rubble pile at all. Perhaps it possesses unusual internal strength. Perhaps its composition differs from anything we have encountered before. Perhaps some unknown process shaped it in a way our current models have never accounted for. But the deeper point here is this. Rubin is not simply finding more objects. It is finding objects that demand better questions. And asteroids represent only one category of discovery. Rubin may also become one of the most powerful instruments ever constructed for detecting visitors from interstellar space. Throughout all of recorded history, humanity has confirmed only a small number of objects that originated outside our solar system and traveled through ours. Oumuamua was the most famous, partly due to its peculiar shape, its unusual trajectory, and its unexplained acceleration. Then came additional interstellar objects, each one a messenger arriving from another star system entirely. Rubin is expected to find more of these, perhaps 5, perhaps dozens, perhaps even hundreds, objects originating from places beyond our reach, arriving unannounced, cutting through the solar system, then vanishing back into the void. They are not ships of any kind. They are most likely natural fragments shed from other planetary systems, but that might be precisely what gives them such worth. They are physical samples from foreign solar systems that travel all the way to us. We cannot easily give chase. We have no way to retrieve them. We may have barely enough time to observe them at all, but Rubin may well be the telescope that catches them before they slip away. Visitors nobody summoned, messengers sent from stars we may never see at close range. A supernova ranks among the most ferocious events the universe has to offer. A massive star reaches the final chapter of its life, collapses inward, then erupts outward with enough force to briefly outshine whole galaxies. For astronomers, supernovae are like cosmic signal flares. They burn bright. They are dramatic. They announce their presence across the breadth of the universe, but there is something stranger still than a star that explodes, a star that simply ceases to be. This phenomenon is known as a failed supernova. Rather than blasting its outer layers outward into space, the star collapses directly into a black hole. No blinding explosion, no breathtaking display of light, no warning flare powerful enough to command the sky. One moment the star exists, then it does not. For decades, scientists have held the theoretical position that failed supernovae ought to exist. But catching one in the act is extraordinarily difficult because the whole event is defined by what is absent. You are not searching for something that appears. You are searching for something that disappears, and that is precisely the kind of mystery Rubin was constructed to uncover. Because Rubin surveys the sky over and over again, it can compare what was previously present with what is currently there. If a star dims, vanishes, or behaves in an unusual way, Rubin can flag it. In its early data, astronomers identified a candidate sitting in the Andromeda galaxy, roughly 2.5 million light-years away, a star that may have simply stopped existing. If that turns out to be confirmed, it could rank among the most significant discoveries ever made in the study of how stars die. Direct proof of a massive star collapsing quietly into a black hole. No explosion, no warning, just a soundless death. That shifts the way we think about black holes entirely. Because if some massive stars collapse without producing a bright supernova, then far more black holes may be forming in silence across the universe than we have ever imagined. Stars may be perishing in complete darkness, entire black holes may be coming into existence without a single announcement. And until now, we may have overlooked most of them. This is the sort of seemingly impossible thing Rubin is able to capture. Not because it peers deeper than every other telescope, but because it watches in a fundamentally different way. It perceives change. It perceives absence. It perceives motion. It watches the universe rewriting itself in real time. And behind all of this lies the greatest mystery Rubin was ultimately built to address: the invisible universe. Everything humanity can actually observe, every star, every planet, every galaxy, every nebula, every asteroid, every human body, accounts for only a small fraction of everything that exists. Dark matter and dark energy are what truly dominate the cosmos. Yet we still have no idea what either of them actually is. Rubin will chart dark matter by measuring how invisible mass warps the light traveling from distant galaxies. For the very first time, we may begin to understand where the hidden architecture of the universe actually resides. A map of invisible mass, a map of cosmic acceleration, a map of the forces quietly shaping reality from behind the scenes. And if Rubin's first few months have already delivered impossible asteroids, concealed stellar rivers, silent stellar deaths, and travelers from other star systems, then the question that follows is genuinely terrifying. What happens once it truly begins watching the entire sky? So what did the Vera Rubin telescope actually capture? It did not capture one impossible thing. It captured a universe that absolutely refuses to hold still. For thousands of years, humans gazed at the night sky and believed what they saw was permanent. Stars locked in position, galaxies motionless in the far distance, constellations that appeared to last forever. A universe so enormous and unhurried that a human lifetime was far too brief to notice any movement. But Rubin is demonstrating that none of that was ever true. The sky shifts constantly, every night, every hour, every single moment. Asteroids wander through the solar system. Interstellar objects pass through our cosmic neighborhood with no warning at all. Galaxies rip smaller galaxies apart and leave trails of stars scattered behind them. Enormous stars might collapse without ever exploding. Hidden black holes could be born in complete silence. And invisible matter may be quietly sculpting everything we are able to see. Rubin did not simply hand us a sharper telescope. It gave the sky something like a memory. That is where the true revolution lies. Because when the same patch of sky is photographed over and over, the universe begins surrendering its secrets through what has changed. A moving point of light turns out to be an asteroid. A vanished star becomes a possible failed supernova. A faint trail becomes proof of galactic violence. A subtle distortion becomes a hint pointing toward dark matter. And once you start holding the sky up against its own past, the cosmos stops resembling a still image. It becomes a living, breathing system. The very first images were already staggering. 10 million galaxies captured in a single photograph. A figure so enormous that the human mind struggles to treat it as anything real. Each galaxy a world filled with billions of stars. Each star a possible solar system. Each system a possible history all its own. And yet that single image covered only a tiny sliver of what Rubin will eventually observe. That alone would have been enough to secure its place in history. But buried deep within the early data was something even more significant: the unexpected. A stellar stream stretching 163,000 light-years from Messier 61. A structure larger than the Milky Way itself, hiding in plain sight until Rubin finally revealed it. More than 11,000 newly discovered asteroids, and the full mission had barely even started. A massive object, 20-25 MN45, spinning so rapidly it should have been torn to pieces, yet somehow holding together. Interstellar visitors moving through the solar system. Fragments from other star systems briefly drifting into our reach before disappearing forever. And perhaps the most haunting of all, a candidate object in Andromeda, suggesting a star may have collapsed directly into a black hole without the dramatic explosion anyone anticipated. A star that did not go out in fire. A a star that simply ceased to exist. That may be the most unsettling category of discovery Rubin is capable of making. Not the arrival of something brilliant, but the disappearance of something that was once there. Because absence itself can be evidence. A missing star can point to a black hole. A distorted galaxy can betray invisible mass. A moving speck can expose a concealed asteroid. A faint stream can expose a system that was torn apart. Rubin is showing us that the universe leaves its clues not only in what glows, but in what shifts, drifts, dims, bends, or quietly vanishes. And that realization changes absolutely everything. Because up until now, so much of astronomy came down to where we happen to point our instruments and when we happen to do it. But Rubin operates differently. It watches broadly. It watches repeatedly. It watches quickly. It watches with memory built in. Every few nights, it returns to the same sky and poses the same question. What has changed since last time? That deceptively simple question may turn out to be one of the most powerful scientific tools ever developed. It may allow us to identify asteroids before they become a genuine threat. It may reveal interstellar objects early enough for proper scientific study. It may catch stars collapsing silently into black holes. It may uncover hidden stellar streams surrounding galaxies, illuminating how cosmic structures grow by devouring one another. And it may help us finally chart dark matter, the invisible substance that holds galaxies together, bends the path of light, and dominates the entire architecture of the universe. That represents the deepest layer woven through this entire story. Rubin was named in honor of Vera Rubin, the astronomer whose discoveries helped confirm that galaxies hold far greater mass than anything we can actually observe. Now, the observatory bearing her name may produce one of the most extraordinary maps of invisible matter ever assembled. A map containing no stars, no planets, no luminous gas clouds, but rather the unseen skeleton underlying the cosmos. The gravitational architecture binding galaxies together. The hidden framework steering how the universe has evolved. The dimension of reality that has shaped absolutely everything while never once being visible. And then there is dark energy, that mysterious force behind the accelerating expansion of space itself. We have no idea what it actually is. We cannot say where it originates. We cannot know whether it will go on forever. But Rubin may help us measure its influence across billions of galaxies and billions of years, stretching back through cosmic history. What that means is the telescope is doing far more than observing asteroids, stars, and distant galaxies. It is watching where the universe is headed. And this is precisely why the earliest discoveries feel so deeply unsettling, because Rubin has barely gotten started. The full survey has not yet begun showing what it is truly capable of. And already we are encountering objects absent from every catalog, structures dwarfing entire galaxies, asteroids that push against the limits of known physics, possible silent stellar deaths, and wanderers arriving from outside our solar system. So what unfolds once Rubin has been scanning the sky for 1 year, 5 years, 10 years? How many inexplicable objects are still buried inside the data waiting to be found? How many stars will quietly disappear? How many black holes will form without releasing a single photon of light? How many interstellar travelers have already drifted through our solar system completely undetected? How much of the universe has been shifting, transforming, and collapsing while we assumed it remained still? That is the terrifying beauty of what Rubin represents. It does not shrink the universe down or make it feel contained. It makes it feel more alive, more volatile, more unresolved. For centuries, human beings gazed upward and perceived only silence. Now Rubin is watching that silence move, and the impossible thing it has already captured may not simply be one asteroid, one star, one galaxy, or one object drifting in from another system. The impossible thing may turn out to be the truth itself. The universe is in constant motion and transformation, and we have only just finished building a machine with the ability to finally notice.